Welcome to EDU World Space.
Here we're going to redo the Bohr model, but instead of having an electron orbiting the hydrogen nucleus with one proton, we are going to let the electron orbit a single electron orbit a nucleus with a positive charge of Z multiplied by positive E. So we're talking about hydrogen-like atoms. So imagine helium stripped of one electron. Think of lithium stripped of two electrons, etc. And there are three parts that go into the Bohr model. There are three formulas, if you will. The first one is basically a circular motion relationship. So we're using Newton's second law on the motion. That says that the force pulling on the electron to the nucleus is equal to mass times centripetal acceleration. And we can write that out because we know that that force is the electrical force, Coulomb's law, which we write as the electrical constant times the product of the two charges with absolute value around them over their separation squared is equal to the mass of the electron, v squared over r. So circular motion. And we are assuming a nice circular path. The second part that goes in is just simply conservation of energy. So you could really do these two parts for any central force. The kinetic energy plus the potential is equal to the total. And here we're talking about electric potential. So we can expand the kinetic energy as 1/2 MeV squared, and the electric potential is negative with the two charges in place over R. And notice there is no whoops, that should be positive. I'm already foreshadowing that one of those charges is negative and the other is positive. But we don't want the absolute value because the sign really matters. Whereas in the force, the sign goes with the direction. And the third thing that goes into the model is the quantization of angular momentum, which is equal to product of mass times velocity times radius. And that is quantized in units of h bar. So what to do with all this? Well, we can flesh it out a little bit more. Usually what's a good thing to do is to take equation 1 and solve it for the mass times the velocity squared. And we'll go ahead and put in our charges. And one of the factors of R cancels. And what we can then do is put this into the energy. And we see something kind of cool happen when we do that. Let's take a look at the energy now. Is 1/2 k z e squared over r minus, that's k electrical. We will drop that subscript. What we notice is that the total energy is 1/2 the potential energy. And this is true for electrical as well as gravitational central forces if the object is moving in a circle. Okay, now what we're after is an expression for the energy and an expression for the radius. And so what we'll have to do is basically get rid of the velocity. Actually, we just want the energy, thankfully. And the way we're going to remove the velocity is by using equations 1 and 3. Okay. So what we need to do is find that energy as a function of n. So our next algebra steps are going to involve use equations 1 and 3, which have the two unknowns r and v in them, and substitute for one in relation to the other and eliminate one of those. Yeah. Okay, so what we want to do is, and that's the way I think I'll do it, is I'm going to use 3 to find v, and then sub this back into 1. Three is a fairly simple thing to solve for v. Okay, so now we can go back and in our number 1 equation, put in MEV squared and it looks kind of like a mess, but let's just be careful with things that we're canceling. And that is equal to KZE squared. KZE squared. Yeah. Over R. Good. Okay, and then we can be very careful to cross multiply, square things out. I think it'll just be easy to bring the R squared over to one side. We'll get a factor of R to cancel. And yes, that will make it easy to solve for R. Yeah, there's one factor of ME that will cancel. And I think that's it for cancellations. I hope. And yes, we'll cross multiply. So there's probably some cleanup we can do, but I'm not sure we need to do any cleaning up. But what this does show us is that the radius gets smaller. So there are a couple checks we can do. So the radius gets smaller as z goes up, which makes some sense, more electrical attraction. And it goes up as n squared. And we know that's true for the Bohr model. Okay, and our last step then is to put the R, just invert it and put it into our energy formula. So we're going to sub into energy and be careful not to lose any good stuff. Okay, so we have a half, yeah, and a z. And then we want to put the inverse of r in there. So I'll carefully write down the denominator upstairs and the numerator downstairs. And I'm already feeling pretty good because the denominator goes as n squared. Oh, yes. And so now simplify it a little bit, clean it up. There's all sorts of things that show up squared. The k comes squared. E squared is squared. The z is squared. And there's an h bar squared. And then there's me over 2 times n squared. Okay, so we can see that the energy actually goes down very strongly. And we can maybe just even clean this up a little bit more and think about that energy as a cluster of constants. Okay, there's the first cluster. And then mass of the electron over 2. And then z squared over n squared. And really, that stuff in the front with all the constants really has a simple interpretation. It's minus 13.6 electron volts. So we can now determine the energy levels not only as a function of the integer n, but as a function of the number of positive charges left in the nucleus. And I do want to reiterate that this model only works if you have a single electron in the atom. So all the others had to have been removed